Hello dear students, how are you all? So, last class we discussed about close packing in crystals. Okay. So, today we are moving for a new topic, that is types of voids. Okay. So, in the packing itself I mentioned the types of voids, right. Slightly I mentioned what are the names of the voids present in different types of close packing, right. So, today we are going to discuss in detail about the types of voids. Voids we can otherwise call interstitial sites or interstitial voids. So, what are the different types of voids present in crystals? Okay, let us discuss. Okay, and the first type is tetrahedral void. First type is tetrahedral void. That one you can show in your hexagonal close packing, isn't it? In 2D hexagonal close packing or in 3D hexagonal close packing, you show more about this type of tetrahedral void, how it is formed. Okay, so do you remember the structure of that one, hexagonal close packing, which is otherwise known as AB type? Do you remember? Yes, I think you all remember because you all already studied the topic and you are all thorough with those topics, right? Yes. So, here this is the first layer. Above the three spheres of the first layer, one sphere is formed in the above the three spheres of the first layer, one single sphere is covered. Then the first layer ഈ voidനെ കവർ ചെയ്യുന്ന രീതിയിൽ നമ്മൾ സെക്കൻഡ് ലെയറിൽ ഒരു സ്ഫിയർ വരുവാണെങ്കിൽ ആ ഒരു ടൈപ്പ് voidനെ നമ്മൾ എന്ത് പറയുന്നത്, tetrahedral voids. Why it is called so? Yeah, yes, while seeing this structure we can see that the three spheres, when you join the centers of these three spheres, you will get a equilateral triangle like this. Okay, the center, the corners of the or you join the centers of the three spheres, you will get an equilateral triangle, and above that the sphere, one more sphere is coming. So, in this they are occupied here, you can see a void here. So, such type of void you can call tetrahedral voids. Here the coordination number is 4, as the name indicates, the coordination number is also 4 here. Okay. So, while seeing the hexagonal close packing, HSCP or cubic close packing, we can see that each sphere consists of two types of tetrahedral void, tetrahedral void. Number of tetrahedral voids is equal to 2 for each sphere. While you looking at the CCP or HCP, you can see that for each sphere we have a 2 tetrahedral voids. So, that is the first type of voids. Then we go for the next type, and the second type is called octahedral void. Why it is called octahedral void? Okay. So, in this close packing you see that third layer is coming on the second layer, above the second layer. So, first layer, second layer, third layer. So, you will see that there occurs a combination of two voids. There occurs a combination of two voids. Okay, that is coming in between the area of the 6 spheres. It comes between the areas of the 6 spheres. That is 3 spheres in the base layer and the 3 spheres in the upper layer. So, you will get a 2 equilateral triangle intersect each other. In between that you can see the combination of two voids. So, while redraw that 2 equilateral triangle, in between that void is formed. So, this is a shape of a octahedron. So, that is why this type of void is called octahedral voids, right. Okay. Here, as the name indicates, the coordination number is equal to 6, and one octahedral void is present for each sphere. Earlier I told you what about the tetrahedral void. For each sphere we have 2 number of tetrahedral voids, but in octahedral void only one octahedral void is present for each sphere. Okay. So, we can say that octahedral void is only half of the tetrahedral void, or it is present only half of the tetrahedral sites. Okay. So, if suppose we are taking n will be the number of spheres, then how many number of tetrahedral voids we have? Yes, it is 2n number of, because each sphere having 2 number of tetrahedral voids. So when we considering n number of spheres are there, the number of tetrahedral voids is equal to 2n. What about the number of octahedral voids? Yes, it is equal to n itself. Okay, so number of octahedral voids is equal to n, number of tetrahedral voids is equal to 2n. So in CCP structure, you see that for we have 8 number of tetrahedral voids and 6 number of octahedral voids. CCP structure you already seen. So while checking those structure, you can see that we have for each CCP we have 8 number of tetrahedral voids and 6 number of octahedral voids. Now calculate the number of tetrahedral voids for single sphere in packing. In CCP packing, we can calculate the number of tetrahedral voids for single sphere. How will you calculate? The formula is number of tetrahedral void around single sphere divided by number of spheres in a tetrahedral void. So what is the formula? Number of tetrahedral void in each sphere divided by number of spheres in a tetrahedral void. So what about the number of tetrahedral voids in CCP? That is equal to 8. Number of spheres for forming a tetrahedral void, just now I told you how many number of spheres we need for forming a tetrahedral void? 4. So that is equal to 8 by 4 equal to 2. So 2 is the number of tetrahedral voids for sphere in packing, for single sphere in packing. Then what about number of octahedral voids for single sphere in packing? So that is the same formula, that is equal to number of octahedral void around a sphere divided by number of spheres for a tetrahedral, for number of spheres for a octahedral void. So that is equal number of octahedral void is equal to 6 in case of CCP. So 6 divided by how many number of spheres we need for forming a octahedral void? Just now I told you we need 6 number of spheres, 6 number of spheres for forming a octahedral void. So both 6 by 6. So 6 by 6 is equal to 1. So number of tetrahedral voids for single sphere in packing is equal to 2, and also the number of octahedral void for single sphere in packing is equal to 1. Okay. So one more type of void is present, that is cuboidal void. So this is formed in the simple cubic closed packing. Simple cubic closed packing, you know, our first layer is arranged, the spheres are arranged in a far apart manner. Okay, there exists a void present, there is a void present. Such voids are called cuboidal void. When you fill that cuboidal void using other sphere, we will get a BCC like structure. So these are all about the voids. So we have how many types of voids? Tetrahedral voids, octahedral voids and cuboidal voids. Okay. So next topic is calculation of packing efficiency. Before moving to the calculation of packing efficiency, we have to know the relation connecting the radius of the spheres and the edge length A. So now first we discuss about the relation connecting the edge length A and the radius of the sphere. So in HCP and CCP structure, we know which is the unit cell in HCP, CCP. I told you FCC unit cell, that is face centered cubic structure. CCP and HCP packing, HCP and CCP packing, the unit cell present is face centered unit cell, isn't it? Yes. So in face centered unit cell, we discussed in our earlier classes face centered cubic. What about the particles present? Where the particle present? And all of the corners and each face centers. So this I am taking only one part, you know, particles present at the corner and center of the faces, right? So suppose you consider this unit cell, this cube. Here the one particle is present at the corner. എല്ലാ കോർണറിലും പാർട്ടിക്കിൾസ് ഉണ്ട്, ഇത് പറയാൻ വേണ്ടി ഞാൻ ഒന്ന് മാത്രം എടുക്കുന്നു. Present at the corner and one particle is present at this face center. ഒരു സൈഡിൽ ഉള്ള ഈ ഫേസ് സെൻറ്ററിൽ ഒരു പാർട്ടിക്കിൾ ഉണ്ട്, and one particle is at the other corner. Okay. So we are calculating the distance between, the relationship between R and A. So what is A? The edge length. This is a cubic structure. So each length will be same. That is edge length will be A. Suppose A will be the edge length, and R is the radius of the sphere. R is the radius of the each sphere. So we have 3 spheres here. So what about the distance AC? ACയിൽ നമുക്കറിയാം ഈ സ്ഫിയറിൻ്റെ പകുതി ഭാഗവും ഒരു ഫുൾ സ്ഫിയറും മറ്റൊരു സ്ഫിയറിൻ്റെ പകുതി ഭാഗവും. So we have R plus 2R plus R. Total 4R. AC is equal to 4R. So I am writing here AC is equal to 4R. So AC 4R ആണ് നമുക്കറിയാം. Okay. So you just consider triangle ABC. Which is the triangle ABC here? ABC. This triangle you just consider. We have to find out what is the distance of AC. You know, by trigonometric theorem, the AC square is equal to AC distance. I can take it as a B, that is small letter B. So AC square, that is B square, is equal to BC square plus AB square. Okay, in mathematics you detailedly studied about this Pythagoras theorem, so need not say about this theory, right? You all know because you are all +2 students, right? So AC square is equal to BC square plus AB square, isn't it? So what about BC? BC is a edge length. This is a cube. As this is a cube, each edge having the same length. So what is the edge length here? Yes, it is A. So BC square is equal to A square. And what about AB? AB is also an edge length. So that is also equal to A square. By seeing this structure, you can you can sure about AB and BC same. But this is a structure of a cube. You know, all the sides are equal. So A square plus A square 2A square. Okay, that is B square 2A square anengil. What about B? Root of 2A square. That is root 2 into A. I told you what is B. B is equal to 4R. 4 into radius of the sphere. 4R is equal to root 2A. Right. So what about R? R is equal to root 2A by 4. Okay. So by simplifying 4 എന്ന് പറഞ്ഞാൽ എന്താ 2 into 2. അല്ലെങ്കിൽ 2 നമുക്ക് root 2 into root 2. So while simplifying you can write it as 1 by 2 root 2A, or you can write R is equal to A by 2 root 2. So this is the relation connecting radius R and edge length A. തിരിച്ചും നമുക്ക് എഴുതാം. What about A? A is equal to 2 root 2R. So this is the relation connecting radius and edge length A for an FCC unit cell, face centered cubic unit cell. Okay, in FCC the relation connecting radius and A is equal to R is equal to A by 2 root 2. Okay, now we go for the packing efficiency in FCC. So next, calculation of packing efficiency. Okay, so what is the formula of packing efficiency? That is equal to volume occupied by the particle divided by total volume into 100. So percentage of packing efficiency is equal to volume occupied by the particle divided by total volume into 100. So in FCC, you know, number of particles per unit cell we studied earlier. What is that? This 4. Yes, we have in FCC unit cell we have 4 number of particles per unit cell. So 4 into, for each particle what is the volume? Here what is the shape of the particle? Yes, we know here we took the shape of the particle as spheres. Volume of sphere, you know, 4 by 3 pi r cube. So this is the volume of each sphere, 4 by 3 pi r cube. So in FCC we have 4 number of particles, that is 4 into 4 by 3 pi r cube. So this is the volume occupied by the particle. We have only 4 particles, that's why. Divided by total volume of the unit cell. What is the type of unit cell? Here the cubic unit cell, shape of the cube. Total volume of a cube is equal to A cube, where A is the edge length. So total volume is equal to A cube. So here total volume A cube. What about A? Just now we derived A is equal to 2 root 2 R. So just you put the A value here, you will get 16 by 3 pi r cube divided by what? 8 into that is 2 root 2 r whole cube. So you will get 8 into 2 root 2 r cube. By simplifying this mathematical equation, the mathematical terms, by simplifying the mathematical terms, you will get 74%. You already discussed in cubic close packing and also in hexagonal close packing, the packing efficiency was 74%. So now you proved that the packing efficiency is 74%. That is, here the unit cell present is FCC. First we have to calculate the relation connecting radius and edge length, and you got the answer that edge length A is equal to 2 root 2 r. Then simply you go for the equation for packing efficiency. Next you calculate which is the packing efficiency. That is, you found to be 74% for FCC. Okay. Next we will move to body centered cubic. So first we find out what is the relation connecting radius and edge length of body centered cubic. Okay. So BCC structure we already discussed. What about the particles? Particles are present at all the corners and one particle at the center of the cube. Okay. So just now you look at this, particles present at all the corners, all 8 corners are the all 8 corners and at the center. Okay. So this is the body diagonal of this cube passing through the center of this. So the distance AF we can call it as a body diagonal. In the later case FCC, that distance we can call as face diagonal. So that was face diagonal. We already discussed the face diagonal is equal to root 2r in the case of face centered cubic. There we can call it as body diagonal. Here we can call it as body diagonal. In the case of FCC we call it as face diagonal. So what about AF? AF distance is the body diagonal, and here this AF distance total is equal to 4r, the half of the 2 sphere and 1 complete sphere. So the distance AFC is equal to 4r. We have to find out this distance first. So first of all we consider a triangle EFD, which is the triangle EFD. And while considering this, the distance B is equal to this is square plus this square from Pythagoras theorem. So we will get A square plus A square, because this side is edge length, also this side is also edge length. And B already we discussed in the case of FCC. One more time I am telling, this B distance is called face diagonal. B already we find out, we got it as root 2a. Here also we can find out. So A square plus A square, B is equal to root 2a we got. Okay. So next we have to find out the body diagonal. So now you consider the triangle AFD. Which is AFD here? Yes, AFD. This triangle you consider. We have to find out the distance AF. So AF square, or the distance you simply C, mark at C. Since C square is equal to this this face diagonal B square plus AD square. What about AD? Edge length, nothing but edge length. So B square plus AD square. B square we already find out, that is 2a square plus a square, so 3a square. So 4r is equal to 3a square is equal to C square and നമുക്ക് 3a square കിട്ടിയത്. So what about C? C is equal to root 3a. So what is C? C is this distance, that is equal to the body diagonal, which is equal to 4r. Simply they can ask a question like this. In BCC structure, what is body diagonal? What is that? 4r. That also a one word question you will get from this. Okay. So what is r? Root 3 by 4a, or you can write a is equal to 4r divided by root 3. Okay. So now we can go for the calculation of packing efficiency. So you know what is the formula of packing efficiency? Yes, it is volume occupied by the particle divided by total volume into 100. That is the formula for calculating packing efficiency, percentage of packing efficiency. Here we have BCC structure. So we already know that in BCC structure how many particles per unit cell are there? Yes, it is 2. 2 number of particles per unit cell are there. So 2 into, for sphere the volume, for a sphere the volume is 4 by 3 pi r cube. So 2 into 4 by 3 pi r cube divided by total volume. Total volume means a cube. You know, you just now find out a is equal to 4r by root 3. So 4r by root 3r whole cube into 100. By simplifying this calculation, you will get it is equal to 68%. While checking the speciality of BCC, we already told that in BCC structure the packing efficiency was 68%. Now we proved it, it is obviously 68% itself. Now we discuss about the packing efficiency of simple cubic structure. Okay. So in simple cubic structure, you know that the particles are present only at the corners. Okay. You already know the particles are present only at the corners. So suppose you consider these two corner particles present. So edge length A, by seeing itself you can clear that the edge length A will be half of this sphere, plus half of this sphere. So edge length r plus r, 2r. So simply you can write A is equal to 2r or r is equal to A by 2. So this is the relation connecting the radius r and edge length A in simple cubic structure. Okay. Now we have to calculate the packing efficiency. You know the formula of packing efficiency, what is that? You already done two problems. What is that? Yes, volume occupied by the particle divided by the total volume of the unit cell into 100. So that is the percentage of packing efficiency, right? Percentage of packing efficiency. Yes, then what is the volume occupied by the particle? In simple cubic structure we have particles per unit cell is equal to, you know, we already derived the expression, that is 1 by 8 into 8. So particles per unit cell is equal to 1, that we already know. So 1 into 4 by 3 pi r cube. 4 by 3 pi r cube is the volume of the each sphere. So only one particle are present in simple cubic structure. So 1 into this divided by a cube. What is A here? You know, A is equal to 2r. So 2r the whole cube into 100. That is the percentage. So while solving the equation, solving the mathematics, you will get 52.3%. So this is the packing efficiency in simple cubic structure. Okay. So we discussed all the three structures, that is in FCC we calculated the packing efficiency, which is that, and in BCC, in FCC what about the packing efficiency? Yes, it is 74%. In BCC we see that it was 68% and in simple cubic it was 52.3% only. So what we conclude by seeing this packing efficiency, we can see that more economic pattern is what? FCC structure, because most 74% is covered. Okay. So now we will go for simple problems. In exams they usually ask problems of this type or calculation of this relation of using the relation connecting A and R. They will ask problems in your final exam, and also in your entrance exam they will ask questions based on these things. Okay. So shall we go for a problem? So now do one problem. So it's a very simple problem. You have lots of problem in your textbook. In your home you can practice those problems. You can practice with those problems. Okay. So while doing the problem only we can understand the theory. Okay. So just do this simple problem. So you just read the question. Chromium metal crystallizes with a body centered cubic lattice. The length of the unit cell is found to be 287 picometer. Calculate the atomic radius and the number of atoms per unit cell. Okay. First of all, we know for body centered cubic lattice, that is BCC. What is the number of particles? Here particles are atoms they gave. So number of atoms per unit cell, you already know. Body centered cubic, 1 at body center and particles at the corner. So what is the total number of particles? 1 at body center plus each corner. We have 8 number of corners, 1 by 8 sharing. These all the things we discussed early, so I am not going for in detail. So that is equal to 1 plus 1 is equal to 2. So that's all about the number of atoms per unit cell. Next they ask the question, calculate the atomic radius. Just now we told what is the relation connecting the edge length and atomic radius. They already gave the value of edge length A, that is equal to 287 picometer. If they are given with picometer, they are given the answer in meter. You have to convert this picometer into meter. Okay. Otherwise you can calculate as such. If the answer is in picometer, need not convert this. Okay. So here what about this is we have to calculate the atomic radius. You know, in BCC structure the body diagonal 4R is equal to root 3a. So R is equal to root 3 by 4a. Okay, just you simplify 3 by 4 into 287. So you will get the answer in picometer. So this is the way, using calculator you can solve this problem, right? So this is the way we have to doing the problem. If the question is in centimeter or meter, you have to convert the picometer in that sense. Okay. So this is a very simple problem. Lots of problem I will give you in assignment. So now the topic is, we are wind upping the topic. So just now we discussed about the packing efficiency in different unit cell. So in this session we discussed about packing efficiency of the unit cell, and we discussed the unit cell like FCC, BCC and simple cubic. All the packing efficiency we calculate. In next class we will have a new topic, and now just for now we will stop here. Okay, thank you.